There's always a small delay where I have to make sure.
I know the drill.
Yeah, it's not your first time. um, I'll just give YouTube 30 seconds to go live.
Sure.
Awesome. We're live. I can hear an echo. Let me close that tab so that I don't feel paralyzed. Uh, Welcome back, everyone. I'm excited to have chai in my Kaggle cup. I have a lot of different chai mugs. I brought out my Kaggle mug to have chai with Jill, as I was reminded of the correct pronunciation. I hope I got that right. I'll be interviewing him for the second time on the show. Jill always gets amazing finishes with his incredible teammates on different sets of competitions, and I'll be learning how he does that across different categories of competition. We learn through his Kaggle profile. If you go there, you'll see those are absolutely different types of competitions. Today, we'll learn about an audio competition called the BirdCLEF. Specifically, it's 2022 version where their team finished 11th. They actually recently moved one position up and got into the goal zone. And we'll be learning about their solution and how did they get there. Jill, thanks so much again for joining me for the second time on the series.
Thank you for having me. I remember last time in our first interview, you said that I was probably going to be a grandmaster by the time we had our second interview. Unfortunately, this is not yet the case, but let's hope for by the time we do a third one, that has happened.
I'm sure it'll be soon the case. You're just one solo gold away from it,
That's
if I'm right.
correct, indeed. Yes.
Sounds great. I was trying to pull up your Kaggle profile. Let me quickly do that. I'm also curious about your Kaggle profile name because it's Group 16. How did that come about?
That is actually a very funny anecdote, to be honest, because I probably explained this in my last interview, like how I got in touch with Kaggle and machine learning. And I said that I was during my first year's master degree that I had a course on machine learning. And within that course, we had to do a project which was hosted on Kaggle. And so we were divided into groups, and every group was just assigned a random number going from group 1 to group 30. And they were like, yeah, you'll have to make a profile on Kaggle so that you can compete in the competition. And clearly, I didn't really understand how you're supposed to make accounts or something. So we were group 16, and I said, "Yeah, I'll make the account to participate in the Kaggle, and I'll name it as I'm supposed to do, group 16." But of course, you can pick a team name in the competition, which is I didn't know that yet. And so yeah, I'm stuck with group 16 now for eternity.
Many people don't like their Kaggle usernames, and I know Kaggle won't give us that option to change the username ever. So it's a
Exactly.
problem.
Luckily, we can change our display name, so that's already a very good thing. But yeah, the Group 16 handle is a bit unfortunate, but yeah, I can live with it.
I think all top Kagglers have a unique name, unique username. So maybe that's one of the secrets.
Maybe, yeah, maybe. I haven't thought of that, but yeah, maybe it is.
So I want to now learn about you've been competing across many different competitions. What's kept you going? Because if I go back to sharing your profile here, you've competed across, from what I understand, on a surface level. So this was a sort of a simulation competition. Then there was the iron switching one, mRNA one. This was another simulation competition. This was an audio one. So why do you keep competing, and how do you like decide which type of competition to join?
Yeah. So, firstly, I keep competing because I find it a lot of fun to compete on Kaggles. I have a very competitive drive inside of me, and that really flourishes within the Kaggle environment. I'd even dare to say that I'm typically intrinsically more motivated for these Kaggle competitions than, for example, a research project, because there is no direct competition, or this leaderboard format is not really present there. And so somehow that really drives me a lot further. So that's the primary reason. If I wouldn't have any fun doing this, then I wouldn't be doing it. But then, of course, there are many other advantages to doing it. So I think I've met already a lot of new people over the years that I participated on Kaggle, and I actually truly feel part of some kind of community. So I got to know many people. We sometimes communicate, whether that be over social media or through some private messages. So that's a lot of fun, and that helped me build quite a good network, I would say, of many data scientists across the world. And then, well, of course, this also, if you are successful in some of these competitions, that really strengthens your CV. So you really have an objective achievement where you kind of outperform many others on the exact same task. And so that's also really nice. And yeah, I learned a lot from it. So about this competition of today, it's an audio competition, and I had zero to minimal experience in that, and I've learned a lot over the past few months doing it. So those are some of the reasons. And of course, I still have the long-term goal, hopefully not that more long-term, but to reach competition grandmaster. So that would really be the cherry on top, and it's something I will keep pursuing.
Will you stop after that, or will you keep going?
No, definitely not. So, but yeah, what I would probably stop doing the second I get my grandmaster status is participating solo in competitions. I actually don't do it often, but I have to start doing it as of now to get that solo gold. But yeah, I don't really enjoy it. I think you learn a lot more about being in a team, but we'll probably discuss that in a little bit as well. So that is something I would probably give up on, doing the solo participations, and I would just go always in a team.
So let's dive into that. How do you pick your teammates? Because you've many people. So as I understand, characters follow two strategies: keep teaming up with the same people. Another one is team up with people who are like near your position in the leaderboard, so that you can like possibly ensemble ideas and move up together. And the other one is like to team up with different sorts of people. What strategy do you follow, and how's it helped you?
Yeah, so I would say there's two types of people. Well, two types of people, that's probably a bad wording, to be honest, but I team up with, for example, people I already know in real life, people that are colleagues of mine, and we're good friends, and we just want to have some fun and learn a bit. And those are many of my former teammates, like Bram Steenwinkel is one of them, and now my four teammates within this competition are all colleagues at Ghent University as well. But then on the other side, I have what you mentioned, indeed, that I'm somewhere in the middle of a competition, and I'm like a bit hard stuck in the silver zone. And I need some more diversity in my solution, or maybe if we're building an ensemble, I need some really diverse models in there. And that's when I do cold outreach to some of the fellow participants on the leaderboard, and I ask whether or not they're interested in joining me. And the first time I did that was in the Liverpool competition. So I reached out to Zidmi, Yves, and Cavo, who were already teamed up by then. They already teamed up very often. And I was a bit higher than them on the leaderboard, but I knew that they have a really consistent history of getting good results. And so I contacted them. We joined up. We went from 26th position to first on the public and third on the private. And then after that, because it was such a great experience and the result was so nice, we teamed up in a few other competitions as well. Even outside of the Kaggle platform, we teamed up quite a bit.
Was this on Zindi or other platforms?
No, it was on Crowd AI. It was an insurance competition, I think, the one we did. We didn't do well in it. It was an extremely difficult problem. It was a car insurance challenge. Let me see if I can quickly find it back, the exact name of it.
I'm trying to do the same as it on the side.
Yeah, it was a bit of a simulation competition. It was rather interesting, to be honest, because you kind of had to estimate the risk that a certain person would have a car accident in the next year, but you also had to determine a pricing strategy based on your estimated risks, and you had to be the most profitable insurance company, as to say. And so they did a simulation about who actually got the car accidents or not. It was all simulated data. And of course, you wanted to include all the people that wouldn't have a car insurance at a good price and exclude the ones that would have an accident in the next year.
I think I found it. Was this the one?
Yes, that's exactly the one. Yes, yes, yes. It was hosted, I think, by a Swiss research institution as well. Um, and I don't know where you would find us today on that leaderboard, somewhere around the 100 spot or something. Not too great, but yeah, it was fun.
So, once you team up with people, you're obviously shooting for gold. Has the leaderboard ever scared you, or have you like ever felt? Can you walk us through once you like feel stuck and ideas aren't working? How do you fight through that? Because I personally like I'm being selfish because I want to learn how to fight through that potentially to improve my scores as I get back on Kaggle.
That's a great question. I don't think the leaderboard scares me, but it does provide very valuable information. If you're like stuck at 26 and you see whether, let's say you're at 80 accuracy somewhere on the leaderboard, and you see the ones on the top having like 90% accuracy with their models, then you know that there is still something in that data that you haven't found yet. It has to be there, otherwise they couldn't get that 10% increase. And so that's when you start working all nighters, just chasing rabbit holes, trying to find that very specific feature or other kind of modeling technique that they have been using. So it doesn't scare me, I would say. I would even say it motivates me more to try to get on top of that.
um there's also a point of like pulling all these all-nighters, right? Because it's intense brain work and you're like feeling sleepy, sometimes you also feel, at least that's my case, maybe it's different for you, you're not at like the highest performance, like your thoughts are somewhat slower while you're sleepy. How, like, why do you keep fighting that? Like, doesn't the thought of like I should just go to bed and leave it here ever take over?
Yeah, that's true, and it is something I try to live by. But sometimes, yeah, the deadline of the competition really puts like a pressure on you that you have to find it as quickly as possible. But in general, I am the first to say go to bed earlier and wake up a bit earlier than you're usually waking up. And yeah, like I'm a morning person, so my concentration is much better in the morning than the evening. So I do try to schedule my days around that specific property of mine. But sometimes, yeah, when the deadline is coming up too close, you do have to work a bit late.
That
It's
makes
also
sense.
especially the case because here in Europe, the deadline of every competition day, where you have a limited amount of submissions per day, it resets around 1 a.m. And I've had many days that I set an alarm at 12:30 in the middle of the night to just wake up and make sure that I make the all the submissions of that day, so that I didn't waste any of the available submissions. And so I would put my models to train, set an alarm at 12:30, go to sleep, wake up, quickly submit them, and go back to bed.
There are all of these little battle stories, right? Like you setting your alarms. I was talking to Nishchay. So in India, the time happens to be 5:30 a.m. So for
Oof.
India, it's literally pulling all nighters because you end up just continuing through that. And people have all of these stories of every day versus also the last week of competitions, which are always really intense.
Exactly. Yeah. Oh wow. Then we're quite blessed here in Europe with just 1 a.m. I couldn't imagine 5:30 a.m. That would be so painful to wake up for, or pulling an all-nighter until 5:30, which is also a long all-nighter.
It's also you wake up in the morning to check the result. You're refreshing the leaderboard. I don't do it. I just like look out for my friends. But it's at 5:30 when that reveal happens.
I wake up many nights, like just how is the leaderboard going, and like quickly checking on my phone. Happened more than once, for sure.
So there's this obsession with all Kagglers, as I've multiple times asked Chris Stewart, and I've learned like it passes through all Kagglers who live by competitions. How do you balance time with this obsession? Like, how do you balance everyday life with this?
Yeah, that's a good question. So I guess I'm a bit in a blessed position to be working at a university. So I do research, and also working at a university gives you a lot of flexibility. So you can kind of fill in your own times. It's not per se a 9 to 5 job, I would say. It has been more than once that I worked in a weekend just to finish up some research projects. So that's already one advantage that allows me to better balance both my work, private life, and Kaggle. But then, yeah, still lots of my free time, whether that be during the evenings or weekends, they are spent on Kaggle. And then I always try to organize competitions to do like a sprint, not really in the beginning, but somewhere around the sixth week or something of a competition, and towards the end of a competition. And in the middle of it, I would typically, incrementally try to improve my model or just run some experiments, but nothing that requires like you to write a lot of new code and that you would have to spend a lot of time on. Like rather try out some different backbones or hyperparameter searching in the meantime. And I always keep track of the public notebooks and the discussions as well. So I do that on a daily basis when I'm participating in a competition, because if some new piece of information is found by someone, then very often this is published either in a notebook or through a topic. And so if you keep track of them, because in some competitions, the amount of notebooks being published or topics being made is hard to keep track of. You need to kind of do it on a daily basis. But by doing that, you kind of learn about these new insights. You can integrate them yourself in the pipeline whenever you want to. And then a final trick that I try to do to balance my time as much as often is like not wasting any computing cycles. So I would always try to have something up and running somewhere. So these, like if it's a deep learning competition, you know that these models, they often train for like 5 to 8, maybe even longer, many hours. And so I would try to like quickly in the morning before I start my regular job, I would quickly set up an experiment, make sure it's running. I would do my job, and I would like have the feeling that I'm still doing Kaggle since my experiment is running somewhere in the cloud. And by the time my regular job is done, the experiment is done as well. I can submit it or do some analysis on it. And that's how I try to balance it a bit.
The last trick I need to learn from you, because the RGB is off right now, as you can see.
Don't waste computing cycles. No.
Awesome. So that concludes the part where I wanted to pick up about your journey in general. Questions. I'd love to now start uh, sharing the problem statement with the audience, and let me share my screen. So this was, I think, the third run of the competition, if I remember
Mm,
correctly.
there's definitely a 2021. I'm not entirely sure if 2020 was organized on Kaggle. I think it was on AI Crowd as well, the 2020 edition. But yeah,
Yeah, I
it
was
has
wrong
been
about that.
running for many years, the BirdCLEF on its own, but only 2 years it has been hosted on Kaggle.
I remember Stefan had. I got confused because I saw the host share papers, and I was literally going through them. So it, I think, goes back to 2015, if not earlier, where they've been running this.
Okay, yeah, but it's also like grouped with many other challenges, like the CLEF
Yeah,
conference is like a conference where all these kind of machine learning challenges are hosted, and they are reorganized every year. And I think it's quite amazing to see how much progress is being made because of this competition format. Thousands of data scientists focusing on the exact same problem. Of course, one of those thousands, yeah, has to come up with something novel and innovative over the years, and that's how such great progress is made here.
yeah. It was also like fascinating to read. Again, I'm going on a tangent, but I was like skimming through the papers for my preparation. Older competitions had CNNs, LSTM, GRU layers. That was like the state of the art, and like they were sharing how hard this was to implement and whatnot.
Yeah,
So
probably like a Diano or lasagna
yeah,
somewhere in the
yes,
beginning. I can imagine the pain.
yeah. So this is like we don't know which version of the competition, but again, second time on Kaggle, and as you can see, it's to identify bird calls and soundscapes. The challenge is there are different species of birds, and you have audio files for that, and you need to, I believe, understand or predict which species of bird is making a sound in that file that you're provided. Is that a correct outline?
Yes, we are provided with soundscapes. So I will discuss that in a bit as well, but it's very different from the training data you're getting. And they are 60 seconds long on average. Sometimes it's like a few milliseconds away from 60 seconds, but let's just say 60 seconds. And then for every 5 seconds, so for example, second 0 to 5, You have to say which of the 21 scored birds occurred or did a call in those 5 seconds.
That makes sense. I'm looking at Rob Muller's
Mm.
EDA from his live Twitch. Let me drop that link in the chat as well for everyone. And I'll just scroll through this to point out anything for the audience if it's of worth highlighting. So again, there's a train metadata file which has more data outside of the sound files. Let me hide this pop-up. Sorry about that. So you get to know about the species and different info around that. Just the audio file is of course not enough for that. You have a subset of species in the dataset that are scored, and the other general stuff, which is the sample submission and test file. Scrolling further, so there are a bunch which have more labels. So, for example, Rob has here pointed out top 20 boards with labels versus bottom 20 boards with labels. So it's not a uniform distribution for all of the birds. And there is also some geographical information. This time, I believe for one of the competitions, it was just Hawaiian birds somewhere in the area.
Yeah, the test data were Hawaiian soundscapes. So the data is from all across the world, but the soundscapes themselves are all recorded on one of the Hawaiian islands. So that's also, again, a huge difference again, in the data.
So was your first idea to delete? Like my idea would be then to delete everything else and just like do Hawaiian training. Was was that considered by you?
Well, I would not have deleted the birds that also appear in Hawaii. Like if it's a bird that's known all across the world,
Mhm.
like Skylar would be one in this data set. This can be in Europe or can be in Hawaii. Well, then even the European clips or recordings are useful because the birds don't sound that different if it's the same species. But
Mm.
if some of these birds that appear on Hawaii um, or sorry, appear somewhere in the world and they do not appear on Hawaii, then that's definitely a good argument to not include that in the training data. But in the end, we actually included all of the provided birds because I do think that the network can kind of learn more general patterns, even from birds that are somewhat irrelevant, that can generalize to these Hawaiian birds. So even by
Mm.
providing it data from completely irrelevant birds, it can maybe pick up some extra signal or patterns in this data. And we're also provided with a very limited amount of data, and these deep learning networks are typically quite data hungry, and so that's why we decided to just feed it all of the data.
That makes sense. Thanks for that clarification. Um, so next up, you also have the author info. We're like looking at the metadata. Not we, Rob had created this notebook. I'm just using that. Um, so as I understand, all of this data is published to Xenocarto XC, where different authors are allowed to publish this, and that's what is being shown here.
Exactly, and we actually completely ignored this piece of information. But I've read in some of one of the write-ups that this guided the cross-validation scheme of someone. So this person would make sure that it's always completely new annotators in the test set within each fold of the cross-validation. And the assumption was, well, that this every annotator probably has its own recording setup, and so that would probably generalize better to the test set, which is again completely different from the training set in terms of quality and how it was recorded. So that was a nifty idea. I haven't evaluated it or how well it would work, but yeah, it's actually, I think, a valuable piece of information who annotated this clip.
Hmm. Sorry, there's like one minor correction. I assumed it's the third competition that, at least by the host, this is the third competition. So earlier it was called Cornell Bird. That's why I missed that one when I
Ah,
looked it
that's
up.
right. Yeah.
And I wanted to, again, side tangent, but some Kagglers, as you would expect from Kagglers, were downloading the entirety of the Xenocarto website, and the host had to make a post. Please don't do that. You're crashing our servers.
Yep, yep,
So,
that's classic Kaggle there. But I do think that the data itself is also a subset from Xenocanto. I think the competition organizers are also the ones responsible for hosting Xenocanto, and I think they use all of the clips that are licensed with like a completely free license, like commercially usage and all that stuff. So that's a subset they take from Xenocanto, I believe.
that makes sense. Um And again, don't scrape the website for data sets. It can crash it. So there are two approaches. I'm not sure if I haven't seen many solutions just feed in direct audio files. Has that changed this time, Jim?
At least not for us, and not in any of the write-ups that I've seen. And there are a few reasons as to why I believe going the way everyone is going today, and maybe, well, it's based on spectrograms, but I'll give some more explanation about that. But you can draw an analogy between a spectrogram and an image, and that gives us a lot of advantages. And the first and foremost advantage is that we can make or leverage pre-training. So we can take weights that were
Hmm.
trained on ImageNet and deploy that or start that, use that as an initialization of our network to start training with. That helps a whole bunch in terms of getting it to a high score. But also the spectrograms itself are much less dimensional than a long audio signal, because typically in audio the sample frequency is really high. I think it's typically around 44,000 hertz. In this competition it was 32,000 hertz. They downsampled it a bit, but so if you take 5 seconds of data, that's already 160,000 measurements, and that is often a bit too large. Like you would need very large kernels or filters in your convolutional nets to really capture enough information, and that would be too parameter intensive. So those are like the biggest advantages of doing it on spectrogram level instead of on the raw waveforms themselves.
Aren't there? I'm sorry, I just haven't looked. So this is a stupid question, but there are no pre-trained weights for audio transformers.
That is indeed something that is somewhat missing in any time series domain. So not only audio, which is also just a time series of very high frequency, but like transfer learning or pre-training is not that common in the time series domain. Nevertheless, we did experiment with well, there was a technique we tried out. It was called YAMNet, but to be honest, that was also trained on spectrogram, but that was pre-trained on a large uh, data set that was from YouTube. It's by Google Research. We experimented a bit with that, but that worked way less than ImageNet, which is somewhat weird. But yeah, ImageNet still seems to be like a good standard for any image problem. And so yeah, transfer learning is somewhat less common in on the raw waveforms.
Interesting. Did you consider, so again, a tangent here, maybe it's a silly question, but I just went to Hugging Face Model Hub and filtered by audio classification
Mm,
models. Did you ever look into this, or was it
no,
again?
and now that you show all these models, that seems like super interesting actually. But we did look at the TF hub, like to get like a pre-trained TensorFlow model to train with Keras or something. Um, but we haven't seen these. Wow. And
They're
yeah,
also quite recent 2021 models with decent number of downloads.
that could have worked really well, maybe. Yeah, we never considered it, and in the end, it turned out that some pre-trained models that were available on the internet could have got you a very high position in this competition. But that's a bit of a spoiler that's coming ahead.
Okay, we'll learn about that very soon. So one more thing I want to point out from here, uh, maybe it's worth experimenting, but it's an idea from me, so take it with a huge grain of chai. It might not work. Feed audio data, or usually, as Jill pointed out, people convert this into a visualization, which is commonly known as spectrogram, and there are different techniques to doing that. And then you utilize ImageNet pre-trained models and just fine tune on top of this to detect. And there are again many, as I understand, minute sampling rates that you can change, and how you create this also that changes a bit of things on how you process it.
Exactly. There are quite a few parameters or hyperparameters to this spectrogram generation, and they have quite a significant impact on the final performance of your model. So that's something we definitely experimented a lot with in this competition.
Okay, that makes sense. I think I just wanted to cover that bit of info from the problem statement. Anything else you want to highlight?
No, I think it was a good quick overview already, and I have some slides coming up that maybe zoom in on a few more of the challenges of this specific data set as well.
Awesome. I'll share your slides and please take it over.
Okay. Let me see. So, all right. So indeed, I'll be doing a bit of a deep dive in our model, and I'll explain a lot more about it in a bit. But before I start, I do want to make a very special announcement because today is actually quite a special day. Today is Sanyam's birthday, and so with that, I would very much like to congratulate you on your birthday. That's something I wanted to get out of the way
Thank
before
you so much.
we go into the technical
Thank
stuff.
you.
My pleasure. Yeah, and a happy birthday to you. And so this is a screenshot of the final leaderboard. So we were first very unlucky, but ended up very lucky to be in the last position to obtain a gold. And as I said, first we were very unlucky because we were actually we finished in position 12 right after the competition. So that would be the highest ranked silver medal, which is the most painful position anyone can finish in, like one spot shy from gold. So we were a bit devastated about the result in the end, but somehow we got a little bit lucky as one of the teams got disqualified. I don't know the reasons, and I don't think it's even important, but we managed to climb up an extra spot and bag that final goal. So that was a really nice result to achieve.
I'll just quickly just wanted to mention this Kagglers profile. So this is Kumar Shubham, and
Yeah.
they actually had like multiple top silver finishes. So I think 4 or 5 of their finishes are
Yeah,
top
I
silver
remember seeing
positions.
that on Twitter that he posted this. I think it was a tweet of Boyan or something where
Abhishek's, I think.
oh, okay. Yes, yes,
Yeah.
yes. Well, that is, yeah. It would be unfortunate to get that once, but getting it like 3, 4, or 5 times is, I don't know. You probably have more chance getting struck by lightning 2 times than having that result. But I did see KS made it to Grandmaster in the end anyway, so that's still good to see.
Yeah.
Uh,
So sorry, I got.
no
I'll
worries.
keep short for the rest of the presentation.
No, no, you can always interrupt me if you have any questions or you would like some clarification. Feel free to ask. I'm sure it helps the viewers as well. So no worries about interrupting me for the remainder of the presentation. And so with this slide, I would like to first thank all my teammates. So again, it is a teamwork effort that got us this result. And so a small presentation about ourselves. So who are we? Well, the names are here. They're like the quite classical Belgian names, I would say. Maar Vic de Grave, Jeroen van der Donkt, me, Gert-Jan de Mulder, and Emile de Prost. Us 5 are colleagues at the Internet and Data Science Lab at Ghent University. I have a little picture of Ghent here in the right bottom. It's a really beautiful city, actually.
That
That's
looks like Hogwarts.
yeah, it's a really medieval, or at least parts of the city are really medieval, and they do make you think a bit about Hogwarts. I do admit that. But yeah, it's a really nice city. If you're ever in Europe, any one of the viewers, I would always recommend paying a visit to Ghent. It doesn't take long to visit as well because Belgium is only very small. You can see every city here in less than a day. Um, And so, yeah, our name was a bit weird, maybe. We were named Kakapu, and maybe a little bit of context about how we got to that name. So, what we did in the beginning, we just Googled what is the dumbest bird in the world because we felt like being the dumbest bird because we all had no experience with any audio data whatsoever. And we noticed that it was Kakapu, which is also a very funny name because poo's in there, and even Kaka is poo in Dutch. And so, yeah, it was a no-brainer. We knew straight away, okay, this is the name. There's no more discussion to be done. And then I already acknowledged all of my teammates, but the solution I'll present today is heavily based on the second place solution of last year, which is also one of the reasons I actually participated in this competition, is that there are many previous versions of this specific competition. And so there was a lot to learn from other solutions already. And that really helps in the learning process that you don't have to discover this by yourself. And I think a quote that is always displayed if you go to Google Scholar, if you look for the paper, is standing on the shoulders of giants. But in this case, on Kaggle, we're standing on the shoulders of probably the best grandmasters at this time in the competition tier. So I knew that this was going to be an amazing baseline to start from, of course. And Julian was actually friendly enough to make a public notebook that implemented this solution already on this year's data. So that's the point where we started from. And indeed, I think a good quick overview was already given, and this somewhat repeats it, I would say. So we need to identify birds in soundscape recordings of 60 seconds. We're given limited training data, and also the training data is vastly different from the test data. And the goal or the usage of such a model would be for bioacoustic monitoring. And that's a way to monitor endangered bird species in a passive, low labor and cost-effective manner. Now, to zoom in a little bit more on the data we're provided. So we're given a data set of 6 gigabytes, which is already not a lot to start from, although the format that was used was heavily compressed. So I think if you uncompress it all or save it as MP3, this would be a lot more storage required. But all of these clips came from about 152 birds, but only 21 of those birds were actually scored or mattered for your score on the leaderboard. Also, the metric details are unknown. We're only given a description about how the metric is somewhat calculated, but the organizers did say us that it would be most similar to macro F1 score, and that would be something you could use for offline or local evaluation. The data is also very imbalanced. So I have a plot here on the right, which is the logarithm of the number of minutes of recordings that we have. I had to take the logarithm already because you wouldn't see many of these bars if I didn't do that. And so it ranges from 41 minutes for the, I'll butcher some of these names, so I'll give a disclaimer, Puyayo bird, and we have 27,700 minutes for the Skylar bird, which is apparently a very common bird in the world. And for every one of those 21 birds and every 5 seconds in a test soundscape, we have to predict with a true or false if this bird occurs in there or not. And so, as I said, the train and test set are vastly different. So there's a huge domain shift. We are actually given rather clean audio clips of these birds, and the call of these birds are rather isolated. So it's really a clip where from start to end, you hear the bird calling. But we need to infer with our model on unclean soundscapes. So really visualize it as putting a mic somewhere in the Hawaiian forests or whatever climate it actually is there, and making a recording of an entire day, and then in the end of that day, having to annotate all of that data. And so there's lots of silences in there. There's lots of background noise. There's actually one test soundscape provided to us without any annotations. But if you would give that a listen, you would already feel how difficult of a data set that was that we need to evaluate on. So you can barely hear any birds. All that you hear is some kind of fire or rain noise. And so that's the data we have to make predictions on. And the fact that we're not given any annotated soundscapes was a bit of a downside to this competition, I would say. So I'll discuss that even more in a bit. But like when we wanted to make post-processing techniques, there was not a single way for us to know which parameters for the post-processing scheme would work best, because we were not given any validation data. And so we had to rely on public leaderboard feedback a lot. And that was quite visible if you just look at the amount of submissions that are made by the gold medalists or even silver medalists on the leaderboard. So I quickly investigated that this morning, and of the last 3 years, I took all the competitions, and then I looked at the gold medalists, at how many submissions they made. The reason I only look at gold medalists is because I know for sure that these people have all committed to the competition and must have put in a lot of time and effort. And we would be here somewhere around 225 competition average submissions being made per team in the gold zone, and that would put us somewhere here in the neighborhood of the rock, paper, scissors competition and so on. So it's one of the top competitions if you look at the average number of submissions being made. And so it was a general strategy of everyone to really make use of that public leaderboard feedback to tune all kinds of post-processing techniques or certain parameters of our pipeline.
Sorry, I want to go on a tangent. You mentioned you looked at gold solutions. So, is that your always like default approach? As I understand, you've not competed on an audio classification competition before this. So, your like first approach was to go and read the previous winning solutions.
Exactly. Yes. So that's what I, especially here, that was a huge blessing that there were so many similar competitions where you could go to the discussion forum over there, really read the write-ups of all of the winners, and then try to implement all of the ideas that they have experimented with. Even the things that didn't work for them were things that we tried out because it's a new data set, a new kind of domain. You never know that something that didn't work out at first now works out today. And so, yes, that's the first thing we did. We looked at all the possible solutions. Exactly. So it's not only the BirdCLEF in there. So there was a rainforest audio detection one.
Hmm.
There have been whale detection on sounds, although those are from 2013. That would be something where I wouldn't look at anymore. Not to pay any discredit to those solutions. I'm sure they're amazing, but that's 9 years ago. The domain has evolved quite a bit since then, of course. So I would typically look at the more recent similar competitions, look at the notebooks and the forums.
That makes sense. So you looked at. I'm sharing my screen for the people listening to audio. The competitions after 2019, maybe these four ones.
Yes, indeed. All four of those we looked at. Like definitely at some point we made a compilation of all the backbones that were used by the solutions, spectrogram parameters. We had an overview of the most popular or most occurring ones. And so we were really compiling all of the insights from all these write-ups manually still. That would be a nice use case for a machine learning model as well.
I want to again, sorry, I want to go on a tangent. So I'm at this stage, as you many people do the same, where like we just look at kernels and tweak those instead of like going back and implementing winning solutions. It, was that ever a gradual change for you, or did you ever jump in and start just implementing winning solutions? Because I struggle to do that right now. That's my question.
I think in the beginning, I actually didn't look enough yet at public notebooks. So I would always try to make something of my own and not look enough at the public notebooks. It's only more recently that I really started looking more at these notebooks. But then I do like copy and paste code from all different notebooks into one single pipeline to really add up to the pipeline. So it's more than just changing some parameters in most competitions. I really try to merge interesting insights or bits from one notebook into the other. But typically, and especially like these competitions where I have to say it's not my expertise in any way, deep learning in general. So that's where I would typically start off with already a published baseline notebook and start extending on that, because chances are very likely that I make some mistake somewhere and then it starts diverging instead of converging the model. So there I go for people that I know that have much more experience than me in deep learning, and go from there.
That makes sense. So it's good to know I'm not following a different approach. Please continue with the presentation.
Yes. So indeed, lots of submissions were being made by everyone. Everyone really tried to make use of their 5 submissions a day. So that's where the alarm setting definitely came in play as well. 12:30 was alarm time to make submissions. Um, and then you already quickly glanced over these spectrograms from Rob's notebook, and we already kind of discussed it as well. So what we typically do in these audio competition is we make a transformation of our data such that we translate the problem from a computer hearing problem to a computer vision problem. And then we leverage all of the research and techniques, of which there are much more plenty within computer vision than computer hearing, and we leverage that. And so the transformation that is being done is called, well, spectrogram transformation. And so we convert this 1D wave into a 2D image, as to say. And I maybe have a few slides on how that actually goes. So what is being done is you go with a window over your audio signal, and you take a Fourier transform of that window at each point in time. And that gives you which kind of frequencies are most present within this piece of audio. That's what these Fourier transforms can do for you. And what we then do is we bin this spectrum of Fourier coefficients. We bin it into chunks of not the same width. So if I'm not mistaken, the human ear is typically much more susceptible to changes when the frequency is low, then that will be very audible to the human ear. While if we're already on a very high frequency, then changes have much less impact. And that's what this MEL spectrogram, so the MEL in that word, takes into account. So it doesn't do equal binning. It will take into account some properties of the human ear. After binning, we can aggregate all of the coefficients in that bin. So we could, for example, take the mean of the coefficients present there, and then we're left over with an image right there on the right, which already somewhat looks like a spectrogram, but it's not entirely there yet. So basically, for each of the bins, we are seeing here the mean amplitude or the mean coefficient strength of these bins. And as I said, this is being done by a windowing approach. Typically, the windows would actually overlap a bit as well, but just for simplicity, it's not done here. So we get this 1D binned representation for each window. And if we start doing this in a windowing approach, we suddenly end up with a 2D image where on the y-axis frequency information is present, and on the x-axis the time information is present.
Sorry, by windowing you mean you pick a few seconds of the audio, right? And you like look at that sample?
Exactly. So it's a parameter. You have a certain window width typically, and then a hop size. So how much do you shift the window after every Fourier transform? And so that's how you go over the entire signal. For every window, you get the binned representation, and you actually just horizontally stack all of these representations together to get your image in the end.
That makes sense.
And so indeed, on the bottom here is a spectrogram generated from the audio signal on top here. And so now that that is out of the way, we can start looking into the training procedure. And as I said, this is very much based on the second place solution of last year. And so what we do is the clips that were provided have varying lengths. So I already showed that the data was imbalanced, but also the length of each clip was also very imbalanced. I think we had clips of just a few seconds, and we even had, I think, one clip that was more than 1 hour long. And so what we did is for each of these clips, we took, or the second place solution of last year, took a random 30-second crop. And to put that somewhat into context, for each clip, we are given a label. But let's just say this 1 hour recording, I don't think there are many birds that can call or sing for 1 hour at continuous time. Their throats would probably be hurting as well. So there is some silence present within that clip. And of course, you do not want to take a crop where you have only silence, because you will associate the label of that bird with that crop. And so you will be confusing your model. You will be feeding it pieces of silence, and you will be saying to the model, it's not silence, it's a skylar bird, for example. And of course, this confuses it. And the 30-second random crop appeared to be a good trade-off between computational requirements. The longer you take the crop, the more computationally heavy your entire pipeline becomes, and the likelihood of actually having at least one call of that bird being present there. So it was very unlikely that it was 30 seconds of silence within those clips. And that's why these 30-second crops were taken.
Did you investigate into like the probability of that? Maybe again, it's a stupid question. Maybe it's like ImageNet where you have like some mislabels, because I assume like you would have some false positives, like 30 seconds we just don't have the sound.
We particularly didn't do it, but in other competitions, I don't think it was that much present within this competition, but they would do some kind of pseudo labeling. So they would do it, train the model iteratively. First, for example, do it on these 30-second random crops, but then they would go in like a 5-second window again over their audio signal and ask the model to predict for every of the 5 seconds. And then you're given some pseudo labels, maybe the probabilities when it's silent within a clip will be much lower than when the bird is actually calling. And that is very useful information to guide the way you crop. It's something we didn't do in this particular way with pseudo labeling, but we did experiment with this audio net I already discussed. It's called the YAMNet, and that's trained on millions and millions of audio from YouTube. And they contain like 5 to 10 classes of bird calling, doves, pigeons, and so on. So we thought it was a very general model and that we could use it just to do like binary classification for every subsequence within the audio to give us like what is the probability that there's actually a bird within this chunk of data. And then we would
Makes
use those probabilities to guide the cropping. So we would only crop where there is a high probability of a bird being present. But it didn't turn out to work very well,
interesting.
probably because the YAMNet wasn't that great in doing the bird no bird classification.
Okay, that makes sense.
And so, as I already mentioned, these audio samples are, well, not recorded at 32 kilohertz, but at least downsampled to 32 kilohertz. So if we have 30 seconds, we can multiply that by 32,000, and that gives us a signal of length 960,000. So quite a long signal, to say the least. And then what is being done, since we need to make predictions on 5-second clips in the test data. For every 5 seconds, we need to say which of the birds are occurring in the test data. But here we're taking 30-second crops, so that's a bit of a mismatch. And so what we do is we further subdivide this 30-second crop into 6 parts of 5 seconds. Then we would generate a spectrogram of each of those parts, and this would be fed into a neural network, which I'll now discuss. This slide contains quite a bit of information, but it gives a good overview, I would say. So on the top, the procedure is visualized that I just explained. So we have our 30-second signal. We cut this into 6 5-second signals. We create a spectrogram. Maybe on the left, I have the dimensions of the data we're working with. And we're assuming a batch size of just 1 here. So we're just doing training on 1 single sample per batch. So as I said, our signal starts off with a length of 960,000. This is divided into 6 chunks. So we can just divide 960,000 by 6 to get 160,000. And then here, this spectrogram transformation happens. And you see that we suddenly have a third dimension where we didn't have that before. And that's exactly because we're converting to images instead of working on 1D waves. And so the 256 is the number of mel bins that we're using. So in how many bins are we dividing this frequency spectrum? And 313 would be associated to the length of your signal, the window size you're using, and the hop size. It all depends on that. So it's not an easy formula to go from this how was 160,000 transformed in 330. It depends on window size, hop size, and your original length. And then here, the greatest advantage of converting this to images comes into play. So we take a pre-trained ImageNet backbone. In this case, SA Resnex 26T, it's always a mouthful, these backbones. 32X4D turned out to be the most successful one, for us at least, on this data. So it's going through there, and as typically is done by convolutional nets, they will downsample the image a lot, and they will create multiple filters of this image. And so in this case, we would end up with 2,048 filters of that image, and only a 10x8 image because of all the mux pooling or any kinds of pooling that is happening within that convolutional net. The image gets downscaled, and we're learning 2,048 feature maps. And
I'm
then,
sorry, I have another stupid question here.
sure, and there are no stupid questions.
So I'm particularly curious. How did you settle on this backbone? Because this is not one of the famous models, right? Was it through the historical solutions? Because I would assume.
Exactly.
Okay.
It
Okay.
was a very common thing in many of the write-ups in last year's solution, and that's why we tried it out. So we definitely also experimented with EfficientNet V2 to be more precise, because that's typically the one that works the best out of the box, I would say, these efficient nets. But that definitely wasn't the case for this specific data set. So we really had bad results with EfficientNet. And so, yeah, this rather exotic one turned out to be very good. We have two more in our ensemble, and they're far from common as well. One's called like ECA NFNet, something I never heard of before, and the
I
other one
haven't.
is, yeah, well, I think many haven't. And the other one is a slight variation on this SE ResNext architecture, where they just have like a wider network with more parameters. It's the 50T one instead of the 26T one, and I think that relates to the output dimension you're getting from it, or it kind of relates to the amount of parameters that are present in that network.
Did you try sexier models like VIT or Connext at all?
Not really. So we mostly limited ourselves to TIM models because
Okay.
yeah, it's the same interface. It becomes really easy to switch backbones. It's you just change a string and it changes the backbone for you. So that's what we mostly experimented with, because there's so many backbones in TIM already that you
Makes
don't
sense.
even have enough time in the competition to try them all out. So we did have to make like a selection. And it's definitely possible that we didn't choose the most optimal one. Definitely, there's definitely one pre-trained net that is much better than the ones we're using here, but we'll get to that in a bit. Uh, and so yeah, we first divided this into 6 chunks, but we are concatenating it back, these chunks. So we stack them in time, and so we'll end up with 2048 features maps of length 60 by 8. And then, and this is also second place solution, they use generalized mean pooling. So they will get rid of the two last dimensions. So for each of the feature map, they would just calculate the mean, and you would be left over with 2048 features. And from there, we applied a dense and a sigmoid instead of a softmax, because it is definitely possible that more than one bird is present within the 5 second snippet. And so it's more of a multi-label instead of a multi-class problem. And that's where you go for a sigmoid instead of a softmax. And so we're left out with 152 probabilities for each of the birds. Then some more details. So each of the audio clips had a quality rating associated to them. It ranged from 1 to 5, and there was a special value of 0 when the rating or the quality was rather unknown. And we ended up, and this was also done by Julian in the original notebook, with all the clips with a rating greater than or equal than 2. We try to include all of the clips, especially the ones with rating 0, because the quality is unknown. It's not per se bad quality. And we also adapted the sample weights based on the rating, but that turned out to not work better. So we reverted this change and just did this as was originally done. We included all of the birds within the training, and so not only the 21 scored birds. The networks were trained, it depended on the backbone and the batch sizes and so on, typically from 15 to 30 epochs, and that would range somewhere between 4 to 8 hours as well. So there was quite an excessive amount of training time needed, even for this limited bit of data. The learning rate was scheduled. Sorry, go ahead.
I was going to ask, this was a training plus inference competition, right? You were supposed to train on kernels, I think.
Exactly. You were never
That
provided
makes
with
sense.
a test set at all. So you just had to hand in a code notebook that did inference for you, and you had to make sure that it ran inference within 9 hours, which seems a lot, but we actually had inference time of close to 8 hours, I believe, in our final ensemble. We didn't do we did some stuff very inefficiently, I think, but it was like in the final days, and we were just adding stuff. checking if it works. And it turned out that we just didn't have enough time to really optimize this pipeline. Otherwise, we could have probably added more models to our ensemble, and that would have maybe improved the score a little bit more as well. So that's something where we definitely could have done better. So it's unlike a submission competition where you're provided with the test data already, you really have to optimize for runtime within these. So you really want your inference to be done quickly, because you're only given a limited amount of time and a limited amount of resources. The Kaggle resources are nice, but they're definitely not great. I think many people have better resources on their own computers or on any cloud providers, but you have to make do with what Kaggle provides you.
I was hiding because I'm one of the people who doesn't utilize them well. But this was a inference competition, so I assume you have to also train on Kaggle kernels, but that's not
Oh
the case,
no,
right?
no,
Okay.
luckily not. So you could external data was allowed, which means you can just add your
Okay.
pre-trained model or the model you trained on the training data as a data set to your inference notebook. So luckily that didn't have to be done. Otherwise,
Makes
it
sense.
would be really difficult to get it in that amount of time. Um, Okay, then some more details. So learning rate scheduling was done by cosine annealing. That's actually something we didn't even experiment with. That is just left as is. The final ensemble consisted of 5 different models, and so they were 3 different backbones. Um, well, I'm not going to pronounce them because they're a mouthful, but 2 of the ESI Resnext and 1 ECA and FNet, very exotic ones, but they did turn out to score really well on the public leaderboard. And we also used 2 different configurations for spectrograms. And so you would think the combination of those 2 configurations with 3 backbones would give you 6 models. But for the Resin X50, that was actually already quite worse than the other models. So we only included 1 of those with 1 spectrogram configuration. And I don't know by heart if it was the left or the right one, but I think the right one, as I see that that's already somewhat more extensively tuned, those numbers. It's not like common numbers that's more on the left. So that's how our final ensemble ended up. And how did we do that ensembling? That was also quite a bit of a challenge, because if we plotted out the, the distribution of the predictions on the single test soundscape that we were provided, we noticed that these distributions were vastly different once again. They were all on the very low end side. So they would all range around predicted probabilities of like 1% or maybe 2%, like really, really low, because there was so much noise in those soundscapes. They were really not
Hmm.
confident, these models. And so the shapes were different, the scales were different. And so we had to think of a way to yes, somewhat be able to take a mean of this. And we didn't want to implicitly give more weight to one of those models in the ensemble just because the distribution is more somewhat to the right than the others. So what we ended up doing was ranking all of the submissions. So if you have a bunch of numbers from 0 to 1, you would basically sort this, and you would assign each row the index in that sorted list. So the smallest number would become 1, and the largest number would become n, with n the number of rows in your data frame. We also tried to just normalize these probabilities to be back between 0 and 1. But then we also noticed that some of these distributions had outliers, while some of them didn't. And so that could have messed up the normalization as well. And we would have to tune normalization per model we're including. And so we went for something quick and simple, and that's ranking the data. It must be noted that by ranking your data, you do lose precious information, as to say. Let's imagine you have a list of numbers, of 1,000 numbers, and your largest number is 10, and your second largest number is 5. Well, then these would get mapped to the number 999 and 1,000. So suddenly the difference between these two numbers is just 1 in a range of 1 to 1,000. So it's actually a very small difference. While before we did the transformation, we knew that the number 10 was 2 times as large as 5. So that really has some information in there, and that is lost by doing the rank data. So Surely this ensembling can be done better as well, but it is something we often do. I also always apply this trick in competitions where area under the curve is the metric, because area under the curve doesn't care about if it's a probability or not. It only cares about ranking. Are you ranking your positive samples greater than the negative samples? And so it's already in there in the definition. It's a ranking metric, and so you can definitely rank your data. And so, as I said, these four first submissions are those SA ResNext low dimension with low amount of parameters, and ECA and FNet with both of the spectrogram configurations. And the final one is the SA ResNext with lots of parameters, but just one of the spectrogram configurations. The four first models score 0.81 on the public leaderboard, and that fifth one only scores 0.79. So that's already a bit of a gap there. And then we took a weighted mean. So we gave them all a weight of 1, except the one that only scored 0.79. We gave that a weight of 0.5. And this is again a situation where this lack of a validation set is really painful. There is no way to tune these weights on Soundscapes because you don't have any Soundscapes. And so we had to tune this by hand or gut feeling. And that's why you don't see any exotic weights in here. It's 1 or a half. So we really had to do this a bit on gut feeling. Well, if you would have a validation set, well, you would tune all of these weights, of course, using SciPy Optimize or something, and you make some moves and the typical tricks, and these were not possible here. And then I discussed the training procedure, but of course we also have an inference procedure, the one we're supposed to submit. And it's quite similar to the training procedure, except that we do not longer work on 30-second random crops, but we take non-random 5-second crops. So we start from the beginning and we go with a sliding window with a shift of 5 seconds across the signal, and we make predictions for every 5-second window. We were also required to give hard predictions, so a true or a false if the bird occurs or not. No probabilities of it occurring, just a true or a false. And of course, all models output probabilities. And you would say, yeah, that's not much of a challenge. Most of these techniques typically always have a predict and a predict proba function. Just use a predict instead of the predict proba. But because the test data was so vastly different from the training data, you would end up with the worst results. It would probably be all falses if you use a predict, which would put a threshold on 0 or 50% probability. It turned out that we had to put this threshold lots and lots lower. And so that was a huge issue, where, or not an issue, but a challenge more, as to say, where many of the submissions, and I think I can speak for all participators, where many of the submissions have been utilized on. So really trying to find this optimal threshold. And we decided, once again, because, and this is also similar to the second place solution, we would know that this threshold would depend on, one, the model you're using. If you're starting ensembling, then it depends on all of the models included in the ensemble. So it becomes difficult to put a hard threshold on these probabilities going from 0 to 1, or ranks after transformation, but the same issue remains. And so what we did was we calculated the threshold using a percentile. So you would plot out all of your data, which is done here on the right bottom, and you would draw a line. Like if you would be calculating the 90 percentile, you would draw a line such that 10% of the data is to the right of that line and 90% of the data is to the left of that line. And last year, the optimal percentile was around 99.8. So really a very low amount of true predictions, because actually the data of last year had many silent moments in there. But this year, and this is mind-blowing actually, and we still don't understand as of why this actually works so well, but the optimal threshold for us was 78. To put that into perspective, we predict 22% of the data to be true. And so if you look at a single clip, we have 21 scored birds that we need to make predictions for. So on general, we would say for 22% of those 21 birds, so roughly 4 birds, that they would be occurring in that 5-second window, which is of course not realistic. There are no 4 birds. That's very rare to see
Yeah.
within 5 seconds. But somehow this did work out well. So by introducing many false positives at a cost of at least having some true positives in there, this did really optimize the leaderboard scored well. But it is mind-blowing. So we have a very high recall and a very low precision model, I would say. So we will say true many, many times, but it will be wrong in many of those times as well. And then, well, the inference procedure is exactly the same as the training procedure, except that we do no longer concatenate in between there, because we want a prediction per 5 second snippet. And we would also start out with a longer signal, 60 seconds at 32 kilohertz, so almost 2 million long. It will be divided into 12 chunks instead of 6, and we would make predictions on them. So that's very, very similar to the training procedure. Then quickly some data augmentations. And here augmentations can be done on two levels. On one hand, you can do it after transformation to the spectrogram. So basically image augmentations is what you would use then, or you can go for waveform augmentations, so sound augmentations, as to say. And we tried a whole bunch of them. And so let's first discuss the waveform augmentations. And already disclaimer ahead, none of these actually made it in the final pipeline of us. Nevertheless, it is interesting and it has been used in previous competitions with success. And I even think that other participants within this competition have used this successfully. So maybe we didn't tune the parameters well enough and so on. But so some typical sound augmentations that you could do would be injecting some noise, and then you have all kinds of noise, audio noise out there, pink, Gaussian, which is white noise, I believe, but there's all kinds of noise, and they're all named after some color. Don't ask me why that is actually, but that is the case. You could increase or decrease the volume of it. You could change the pitch of the audio. You could also introduce some short background noises, and this is something we spent quite a bit of time on. So we used the Free Field 101 data set, which was used in some kind of other competition, not on Kaggle. And the goal there was just to make a binary classification between bird versus no bird. And so we basically used all of the no bird clips from that competition, and we tried to inject it in the waveform as well. Because once again, if you really listen to the single test soundscape we provided, you can only hear rain or fire and not birds. And so we really wanted to kind of mimic that, like introduce rain noise, rain sound, which was present in there. We wanted to really add that to our audio data. And qualitatively, it looked really nice, but it turned out the model didn't perform any better. What did work out very well for us are spectrogram augmentations. And so we did two. One of them is once again just as is from last year's competition, and it's a very generic one for images, as to say, and that's the mix-up augmentation. Just to sketch this really quick, what is done on mix-up? Well, it's rather simple. You take two images with two different labels. They can be the same, but they can be different as well. And then you just take a weighted mean of these two images. So on the right, we will have our new image, and this would be 0.6 times the one on the bottom plus 0.4 times the one on the top. And we also adjust the label information according to that. So this would no longer be an Akiki or an Akiapo sample. This would be a 60% Akiki and a 40% Akiapo sample. So we would really not have a 1 and a 0 in our label vector, but floating point numbers, which is also a bit of label smoothing, which often helps us as well. And then this one worked really well for us as well, but it's really, really simple. So we just masked some frequency bands. So that would be the horizontal lines in the plot on the right, and some time bands. So that would be the vertical lines in the plot on the right. So it looks a bit like a Scandinavian flag, but this is actually the technique called spec augment. And it was published, I think, somewhere last year by Google Research. And then we also spent lots and lots of time on some post-processing tricks. Again, drawing information from solution write-ups of last year. So they're actually linked in the bottom, but this is an idea that came from probably many, but I've read it from CPMP, who's often here as well, actually, on this show. And he had two nifty techniques for post processing. The first one was, you have 1 minute of data, and let's just say that between seconds 5 and 10 you hear a certain bird. Let's just call it bird A to not have to pronounce those difficult names. Well, then it's very likely that this same bird will occur in the nearby future as well. And so what CPMP did in that competition is, if we had a high likelihood of bird A in one of the 12 clips coming from the 60-second soundscape, well, then we would increase the likelihood of that bird appearing in all of the 11 other clips as well. So you would put a threshold on the probability to be certain enough that a bird occurs within the soundscape, and then you would increase the likelihood of that bird appearing across the entire soundscape, making the assumption that a bird doesn't fly there, just does one call for 5 seconds and flies away to never be heard again, which is a reasonable assumption. A second thing that we experimented a lot with was calibrating or predictions based on co-occurrences. So Hawaii consists of 4 different islands, and some of these birds actually appear only on a few of those 4 islands. So in other words, some birds would never appear together. And so if your model is outputting high probabilities for 2 birds that actually never appear together, maybe they hate each other, or one's a predator of the other, or something like that, well, yeah, then you kind of need to recalibrate for that. And that's something we experimented with as well. So you can do it both ways. If a bird occurs very frequently with another bird, then it is very likely that this other bird will be present in the soundscape as well, and vice versa. If some birds never co-occur, well, then it's very unlikely that they will have high probabilities in the soundscape. So this was also an idea of CPMP. And on the left, you can actually see the co-occurrence matrix for the 21 birds within this data set. And so an example would be that the biped bird and the Akiapu bird, you would never see them in the same habitat. I think because biped is a seabird and the other one is more of a mountain bird. I did a bit of research in these birds, but not too much.
So, sorry, to understand, you hard coded all of this, and once the probabilities are out of the model, then you hard code and check if these are the probabilities. You just manually remove all of that.
Yeah, we try to do it in a somewhat of an automated manner, but there were some parameters associated with it. So the first one would be, what is the threshold, or what probability do you expect from the model in order that you are certain that this bird would appear? So for example, in last year's competition, they would say if there's a probability higher than 90%, well, then let's say that this bird actually appears in there. And then another parameter would be, now, how much will I be increasing the birds that co-occur with this specific bird, of which I'm now certain that it occurs? And the other parameter would be, how much would I decrease the non-co-occurring ones? And then how much, because these are also probabilities and not just true or falses, how much percentage do they need to co-occur before I start increasing it? And so these are all parameters, and these would all be easy to tune on a validation set. But once again, it was not there. And so again, we try to think of the most parameter-free way to do this post-processing. So really minimize the amount of parameters that we should tune. And then we had to do it based on leaderboard feedback. Well, in the end, these two were 2 parameter heavy to actually make it work consistently on the leaderboard. So I do think we applied this one in our final submission, but this was actually only our 3rd best submission on the private leaderboard. And so the 2 that are above it didn't use this. So we actually decreased our score on the private leaderboard by doing this. And this one wasn't successful either on the public or the private leaderboard. But then the last one was very successful. And this is also the reason, but once again, we did this very inefficiently, I believe, but was the reason that we had such a long inference time. So I explained the entire training procedure, where we would take like a chunk of 30 seconds and we would do the entire pipeline on it. But in the end, we also shifted this 30-second chunk with 1.5 seconds to the left and to the right. And we did the same pipeline on these 3 pieces of data. And then we took a weighted mean of the probabilities coming out of it. So we would have an original 30-second crop, which would be P0 here in the middle, for example, going from second 25 to 30. And then we would have the ones shifted to the right or to the left on top of it. And then once again, you see like no exotic numbers here, so really gut feeling based parameters. This was, by the way, an ID from IAFOS from last year's competition. And so we ended up using the same weights as him, which are far from exotic. You pay most attention to your actual chunk and you give a little bit of attention to the shifted ones. And that's how we ended up with like a final probability. Exactly. Iafos also got a solo gold medal, by the way, in this competition. I think he ended up 8th or 9th somewhere.
7th, I think, because everyone moved on. Yeah.
It was a really strong solution because he jumped a lot from the public to the private. So he had a really robust solution. I think he scored 0.79, both on public and both on private. So 23 spots indeed. Quite the jump.
Wow, he moved up 23 positions and in just 25 submissions.
Exactly. He only participated in the last week, I believe. So quite insane, an insane achievement from him. Definitely. Okay, I'm almost there, by the way. Then there's another list. I already discussed many things that did not work. I did discuss them because I believe there is merit in most of these things. They just unfortunately didn't work either on this data set because of the domain shift or because there were too many parameters to tune. So we also tried just first training on all 152 birds and then fine-tuning for a bit more epochs on only the 21 scored birds. That didn't turn out to work better in the end as well. We used a weighted loss function at some point as well. So I already said we weighted our samples based on the quality rating of the clip, but we also try to weight the samples or the loss function based on that data imbalanced. Because as I said, the data or the metric being used is similar to macro F1. So they calculate F1 score per class and they would take the mean of all those F1 scores. So every class would have the same impact on the final metric. And so you want to do well for all classes, even the minority ones. And so, yeah, even giving more weights to these minority classes didn't help for the final score as well. And then YAMNet that I have already discussed, we use that out of the box to make predictions on all of the training data. And then we guided our cropping technique or our cropping procedure with these YAMNet probabilities. Didn't turn out to work. And that I did already mention. We also tried including more audio clips than only the ones with a rating greater than or equal than 2. We gave them lower sample weights as well, but it didn't turn out to work either. And then as a final thing to discuss, this Kaggle competition had a little bit of commotion involved as well. And yesterday I was actually reflecting on that, and I noticed that every single one of the competitions that I achieved the gold in had some kind of drama or commotion associated to it. It's maybe a bit of a strong word, commotion, but at least a bit of a discussion to have after the competition. And so the one we won earlier this year, the Google Brain one, but there we managed to reverse engineer the data generation process for 66% of the data. So that was definitely not the goal that was set out by the organizers. Then in the second one, where we achieved 3rd position in Liverpool, there was a leak in the data, but only in the private data and not in the public data. And 2 teams managed to pick up on that. Kudos to them, of course. That requires some very good data analysis skills to actually find that leak, and they did it. But that caused us to drop from spot 1 to spot 3. So that was also very unfortunate as a finish. The open vaccine one, where we ended up 4th, was a really funny one because the private leaderboard was wrongly calculated. They made a promise in the beginning: we are not going to evaluate on samples for which they again had all the quality score associated to them. So they said we won't evaluate on samples with a lower quality. But in the end, they actually evaluated on all the samples, even the ones with the lower quality one. So then we really had to speak out and say, no, this was written in advance that you would not do this. We fine-tuned or procedure based on this assumption, and they had to recalculate the private leaderboard. And we jumped from 200 spot to fourth. We were also third on the public leaderboard, so we were expecting to end up in the gold at least. Then the halide, not that much commotion, but that was a simulation one. So in the end, you have like a week where games are simulated, and we were constantly hopping out of the gold into the gold. It was like every time I refreshed the leaderboard, we were in the gold or out the gold. So nail biting final phase. And then this is where this competition comes into play. A little bit of a discussion that we had as well, because as it turned out, the organizers had a model somewhere on the GitHub repository, and you could clone this and just do inference with it because the 21 scorebirds were already in there. You didn't have to train it, you didn't have to do anything, and you would get the second place in this competition today. So it's a Git clone, predict with that model, submit it, and it's second place. And so that model is called BirdNet, and it's it's from the organizers themselves. And apparently this is trained on lots and lots of data. At first, we also thought this was trained on the test data they were actually using in Kaggle, but that didn't turn out to be the case. And so two teams, again, discovered this. And once again, nothing to blame for these participants, of course. Kudos to them. They did the research. They found the repo. They experimented with it, find that it worked. They contacted the organizers and got explicit permission. So kudos to them, but always painful, of course, to see that you've spent hours and hours training models, but you could be cloning one to predict with it, and you're done. You have a gold in the bag. And so, yeah, with that, I'd like to conclude it. And so the entire talk has been about birds. So this is a shameless plug to follow me and all my teammates on the Bird platform as well, where we're all present.
That's awesome. Let me also highlight at least your profile where we can later send people to here. I'll just do that in 1 second. Thanks for this amazing overview. And I think it's also more satisfying to go through the struggle of training the model than just cloning. I mean, it's of course like really smart people discovered it, but I assume this approach was more satisfying just from the point of efforts.
Exactly. And I do have to say that the first place did much, much more than that. And even the second place experimented with many, many models. But I do think their final best submission was solely BirdNet, because they were kind of scared, I believe, to include it in their ensemble. But the first team included it in the ensemble. So they have many, many other strong models in there as well, which is why they got first place. So definitely kudos to them.
Makes sense. Awesome. I just have one last question, which I usually try to. It's a similar question, which I always ask. What's your advice on learning today for anyone who's shooting for gold?
Yeah, so it's a learning process, right? You can't really expect to win gold, especially if you go solo from your first get-go. So it's a learning process, and then my advice is like always the same. You better start today than tomorrow, because it is a learning process. There will go some time over it. And so if you sign up to Kaggle today and start participating in your first playground competition, even if you're a bit scared from the features, but even there you can definitely participate and learn stuff, I would say. But do it better quicker than later. So there goes time over it. You will develop yourself, you will develop your skills, and in the end, all the hard work will pay off, and you will have opportunities where you can get that gold medal. But also don't expect that every competition you will be able to get that gold medal. You do need that factor of luck a little bit as well. I'll be the first to admit that you need some luck, because as a data scientist, you're trying thousands and thousands of IDs. And if you're unlucky, none of your IDs actually work out. And if you're super lucky, your first ID is the gold winning ID of the competition. So there's a bit of luck involved there as well.
That's great advice. I want to wrap up, but is there anything we missed or anything else you wanted to highlight during this interview?
No, I think we covered most of it. So thank you for all the interesting questions, and I really enjoyed being here once again. Thank you for inviting me as well. As usual, it's always an honor to be here. Seeing the legends or people that I look up to that have been here before me, it's always a pleasure to be here.
No, it's always an honor to share your learnings and incredible people's learnings on the channel, and I'm really grateful people like you keep sharing that. So I'll again request everyone to find all of your teammates' profiles on Twitter and follow them there. I'll also highlight the link to Gilles' profile. If you go there, you can find his Twitter profile as well, and his LinkedIn as well, and his website. So quickly highlighting that as well here. If you just go to Kaggle/group 16, which is easy to remember, you can find him and follow him on all social medias.
That's true. That's actually an advantage of my mistake of taking Group 16. That's much easier to remember than I would pick my real name, because a Belgian name is like a bit exotic to other people, of course. It's harder to remember, definitely.
Awesome. Thanks again for your time. I'll leave this screen share on and I'll wrap up this here. But Jill has also kindly agreed to host the AMA for my birthday, which we'll do on another video in a few minutes. So please feel free to join there if any one of you is interested. Thanks again, everyone who's watching live and watching the recap. And of course, huge thanks to Jill for doing this.
Thank you for having me. And thank you indeed to all viewers that made it to the end. Thank you for your interest, for sure.